Ever wonder what would happen if, like, we could hit rewind on scientific history? Like, what if some of those groundbreaking physics discoveries happened in a totally different order? Kind of what we're diving into today, exploring physicist Robert Close's paper, A Time Traveler's History of Physics.
It's a fascinating thought experiment. Close argues that the way we understand the universe might be very different if, say, we'd figured out the whole wave nature of matter before we went looking for the ether.
Okay, rewind for me here. Most people think of the ether as that thing scientists were wrong about, right? Like, light doesn't actually need a medium to travel through.
Exactly. But imagine if de Broglie, the guy who proposed that matter has wave-like properties, had come first. We might have interpreted experiments about the ether in a completely different light, so to speak. Those experiments, instead of disproving the ether, could have been seen as proof that matter itself is wave-like.
Whoa! It's like those optical illusions where the same image can look like two different things depending on how you see it.
Precisely. And Close starts his paper with this great quote from Thomas Jefferson. "Ignorance is preferable to error, and he is less remote from the truth who believes nothing than he who believes what is wrong."
Oof, that's a bold statement. But it really sets the stage for this whole idea of challenging what we think we know. So is Close saying everyone before de Broglie was wrong about the ether?
Not necessarily. He's more interested in exploring how our assumptions, shaped by the order of discoveries, might blind us to alternative possibilities. Take Aristotle, for example. He saw the ether as this fifth element alongside earth, air, fire, and water.
Right, the ancient Greeks loved their elements.
They did. And this idea of a fifth element, something that permeates everything, really stuck around. Centuries later, Descartes envisioned light as a disturbance in a universal plenum, his version of the ether. He even thought planetary motion was caused by vortices in this plenum.
So even the brilliant Descartes was trying to make the ether fit his worldview. But not everyone was on board with this whole light as a disturbance idea, right?
You're thinking of Newton.
Had to be. He was kind of a big deal.
To say the least. Newton favored a particle theory of light. He was convinced that light traveled in straight lines like tiny projectiles. And to explain things like polarization, he believed that these light particles must have some kind of orientation.
Okay, so we've got the wave camp and the particle camp facing off. But hold on, how did they even know light could be polarized? That sounds like some high-tech stuff.
It's actually simpler than you might think. Back then, they discovered certain crystals called birefringent crystals that could split a beam of light.
Like a prism.
Similar, but instead of splitting it into a rain cloud, these crystals create two beams of light, each vibrating in a different direction. It's like, imagine shining a flashlight through a picket fence. Only light waves vibrating up and down can make it through. That's kind of how these crystals work. But instead of a fence, it's the crystal structure that filters the light.
That's a great way to picture it. So this birefringence thing really threw a wrench into Newton's particle theory.
It was a big clue that something more was going on with light. And then in 1675, old Römer came along and really shook things up. This guy was way ahead of his time.
Hit us with it. What did Römer do?
He actually measured the speed of light, and pretty accurately considering the technology they had back then.
Wait, how do you measure something that fast? Did they have like super accurate sundials back then?
Not quite. Römer was observing Jupiter's moons. He noticed that the eclipses of these moons seemed to happen at slightly different times depending on where Earth was in its orbit around the sun.
Okay, so how does that tell you the speed of light?
Well, Römer brilliantly deduced that this time difference was due to the extra distance the light had to travel when Earth was farther away from Jupiter. It was like noticing that a train whistle takes longer to reach you when the train is farther down the track.
Mm-hmm.
By carefully timing these eclipses, he was able to calculate a surprisingly accurate estimate of the speed of light.
That's some seriously impressive scientific detective work. But how did this tie back to the whole wave versus particle debate?
The fact that light had a finite speed, that it didn't just travel instantaneously across space, provided more support for the wave theory. Think about it. Sound a wave takes time to travel. Light, if it's a wave, should too, and Römer proved that it did.
Okay, that makes sense. So the evidence for light being a wave was piling up. But Newton was such a titan of science, I bet people were hesitant to completely dismiss his particle theory.
Absolutely. It took a while for the wave theory to fully take hold. And even then, there were still some big questions like, what exactly was this medium that light waves were supposedly traveling through? Enter Fresnel and McCulloch, two brilliant minds who tried to make sense of it all.
Okay, let's hear about these guys. Who were they, and what did they contribute to this whole ether mystery?
Well, they were trying to figure out how to model the ether as an elastic solid. They figured if light is a wave, it needs something to wave in, right?
Right, like ripples on a pond. The water is the medium that lets those ripples, those waves travel.
Exactly. So Fresnel and McCullough imagined this invisible, jiggly substance permeating everything, and they tried to work out its properties, how stiff it would need to be, how it would interact with light waves.
Okay, that's pretty creative. But wasn't there a problem? Didn't they run into some snags trying to make this ether thing work?
You're catching on. One of the big challenges was explaining the lack of longitudinal waves in light.
Hold on, rewind for me again. There are different types of waves.
There are. The simplest way to think about it is to imagine a slinky. If you stretch it out and shake one end back and forth, you create a transverse wave. The coils of the slinky move up and down, perpendicular to the direction the wave is traveling.
Okay, like those ocean waves we were talking about earlier.
Exactly. But with a slinky, you can also create a different kind of wave. If you push and pull one end of the slinky along its length, you create a longitudinal wave. The coils bunch up and spread out parallel to the direction the wave is traveling.
Interesting. So what kind of wave is light?
Well, that's the thing. Light only seemed to act like a transverse wave. They couldn't find any evidence of longitudinal light waves, which was a real head-scratcher, because their models of the ether, as an elastic solid, predicted that light should have both types.
It's like they ordered a pizza with pepperoni and mushrooms, but it showed up with only pepperoni. So what did they do about it? Just ignore the missing mushrooms? I mean, longitudinal waves.
Well, McCullough came up with this really wild idea. He proposed a rotationally elastic ether.
Oh, what now? That sounds intense.
It is. Essentially, he imagined an ether whose energy depended only on its rotation, not its linear displacement. Don't worry too much about the specifics, but this idea allowed him to explain light's transverse nature while avoiding those pesky missing longitudinal waves.
I mean, you have to admire the creativity, right? They were bending over backwards to make this ether thing work.
They were. And their work, even if some of it seems a bit out there in retrospect, laid the groundwork for future breakthroughs.
Yeah.
Speaking of breakthroughs, let's talk about James Clerk Maxwell, the maestro of electromagnetism. Even he, the guy who figured out that light is an electromagnetic wave, couldn't shake this idea of an ether entirely.
It's like after all that work Fresnel and McCullough did, the ether was just too ingrained in everyone's thinking to completely disappear, even with Maxwell's breakthroughs. So how did he picture the ether?
Well, it's almost ironic. Maxwell, who unified electricity, magnetism, and light into one beautiful theory, still pondered the nature of matter and its relationship to a deeper underlying substance. He even speculated the matter itself might be made up of affections of some other substance. It's like he was foreshadowing the idea that maybe, just maybe, there's something fundamental underpinning it all, something like a wave-carrying medium.
Talk about foreshadowing. Because around the turn of the 20th century, things got really interesting, right? I mean, we have Thomson discovering the electron, Planck quantizing energy. It's like the whole world of physics was being turned upside down.
It was a time of radical shifts in thinking. And right in the thick of it, you have Sir George Gabriel Stokes, a brilliant physicist expressing this almost poetic longing for the day when we could describe electricity with the elegance of wave equations just like we do with light.
So he was team wave all the way.
Absolutely. Stokes truly believed in the power of the wave perspective. And you know what? In this alternate timeline, Close lays out, he was kind of onto something.
This is where it gets really interesting, isn't it? Tell me more about this connection to Close's reimagined timeline.
So remember how Planck came along and threw everyone for a loop with his work on blackbody radiation?
Vaguely. It had something to do with how objects emit light at different temperatures, right?
You got it. Planck found that the energy of light isn't continuous, but comes in discrete packets, or quanta. Imagine a vending machine that only dispenses bags of chips, not individual chips. That's kind of how light energy works, according to Planck.
Okay, that's a good analogy. So how does this connect back to Stokes and his wave streams?
Close argues that Planck's discovery of these quantized energy levels actually aligns really well with a model of matter as soliton waves.
Soliton waves. Okay, you're going to have to break that down for me.
Imagine a wave that can travel long distances without dispersing like a pulse of energy holding its shape. That's a soliton. Now picture matter itself being wave-like, and these waves can only exist in specific quantized states, kind of like those quantized energy levels in atoms that Bohr proposed.
Okay, I'm following so far.
So if matter is made of these soliton waves, and these waves are quantized, then when they transition between those states, they would naturally release or absorb those discrete packets of energy, those quanta, that Planck observed.
Wait, so light's quantum nature wouldn't be some weird exception to the rules? It would be a natural consequence of matter itself being made of these quantized waves.
Exactly. And it's here where closest alternate timeline starts to get really wild. Because now we have to reconsider Bohr's model of the atom. You know, the one with electrons orbiting the nucleus like tiny planets.
Yeah, that one's pretty iconic. So how does that model hold up in a world where matter is fundamentally wave-like?
That's the million-dollar question. In our timeline, Bohr just kind of stated that electrons could only occupy certain discrete orbits with specific energy levels. He didn't really explain why. But if de Broglie had come first, if the wave nature of matter was already an established concept, Bohr might have interpreted his findings very differently.
Instead of these electrons jumping between fixed orbits like tiny planets switching lanes, you're saying he might have pictured them as waves. But what would that even look like?
Imagine those musical notes you can play on a guitar string. You can only play certain notes because only certain wavelengths fit perfectly along the length of the string. It's like those waves are allowed while others get canceled out.
Okay, I'm picturing it. So you're saying those allowed waves on the string are like the quantized energy levels in Bohr's model.
Exactly. In this alternate timeline, instead of picturing electrons as tiny balls jumping between fixed orbits, Bohr might have seen those energy levels as representing the only allowed wavelengths for electron waves that could exist around the nucleus.
So instead of planets, we have electron waves, kind of like those standing waves on a guitar string, vibrating at specific frequencies determined by the atom's structure. That's way cooler than tiny planets. But what does this wave-based view mean for some of those other big physics concepts? Like, what about the Michelson-Morley experiment? You know, the one that supposedly disproved the ether?
Right. That's a great example of how this reimagined timeline changes our entire perspective. Remember, Michelson and Morley were trying to detect Earth's motion through the ether. That invisible medium everyone thought light traveled through. But their experiment came up empty, suggesting no ether.
Which was a big deal for Einstein and his theory of special relativity, right?
Exactly. But in Close's alternate timeline, where matter is fundamentally wave-like, that experiment would be interpreted entirely differently. Instead of disproving the ether, it would actually be seen as further proof that matter itself is wave-like.
Wait, hold on. How does that work? That seems backwards.
Remember how we talked about measuring the speed of sound? If you're on a moving ship and measure the speed of sound using instruments also on that ship, your measurement will be the same whether the ship is moving or not. Your frame of reference is moving along with the measurement tools.
Okay, I'm starting to see it. So you're saying that because we're made of matter, and matter is wave-like in this alternate timeline, any attempt to measure the speed of light using matter-based instruments would be like trying to measure the speed of a wave using another wave as a ruler.
Precisely. It becomes a self-referential system. So the Michelson-Morley experiment in this wave-based universe wouldn't be seen as disproving the ether. Instead, it would simply be telling us that our measurements are inherently relative to the medium we're made of, which aligns with the idea of a solid ether.
Mind blown. But if we're tossing out Einstein's whole space-time as a fabric thing, what happens to all those mind-bending relativistic effects like length contraction and time dilation? Do those just disappear?
Not at all. In fact, they make even more sense in a wave-based universe.
Yeah.
Those effects, which seem so strange from a classical physics perspective, naturally emerge from the properties of waves themselves. Remember those Lorentz transformations we talked about earlier?
The equations that describe how space and time get wonky at high speeds.
Yes. Well, those transformations, along with the concepts of length, contraction, and time dilation, arise naturally when you think about how waves interact with each other. It's all about how those interactions change depending on the relative motion of the observer.
So instead of being weird consequences of curved space-time, they're just how waves behave when everything's made of waves.
Exactly. Even Henri Poincaré, who did a lot of work on the principle of relativity, the idea that we can only measure relative motion, not absolute motion, would probably be nodding along in this alternate timeline, seeing his ideas reflected in the very fabric of the universe.
Okay, this is all pretty mind-bending, but I have to ask, what about Einstein? Where does he fit into all of this if we're rewriting the rules of relativity?
That's a question Close grapples with in his paper. He suggests that if Einstein had entered the scene when this wave-based view was already mainstream, he might have taken a completely different path. Instead of focusing on curved space-time, he might have developed a theory of gravity based on this wave-carrying medium, this ether.
It's like Einstein is suddenly free to explore all these new avenues, new ways of thinking about gravity, light, even matter itself.
Precisely. And it's not so far-fetched. when you consider that even Einstein himself, later in his career, acknowledged the compelling arguments in favor of an ether.
Whoa, really? Einstein was Team Ether. I never knew that. So how would this ether-based gravity even work?
Think of it this way. Instead of objects being mysteriously attracted to each other across empty space, imagine them influencing the density of the ether around them.
Okay, so more mass equals denser ether.
Exactly. And just like light travels slower through denser materials, think about how light bends when it passes from air to water. In this model, light itself would travel slightly slower through regions of denser ether.
And this variation in the speed of light is what we experience as gravity.
You got it. It's not about curved space-time. It's about the curvature of the ether itself. Objects aren't being pulled towards each other. They're simply following the path of least resistance, so to speak, through this variable density ether.
That's an amazing way to reimagine one of the fundamental forces of the universe. But hold on, I thought wave mechanics was notoriously difficult to work with, mathematically speaking. How do you even begin to calculate something as complex as gravity using waves?
Well, that's where Close's work gets even more fascinating. He actually derived a mathematical framework for understanding how wave mechanics can give rise to quantum phenomena, potentially even gravity itself. He started by deriving a Lagrangian density for rotational waves in an elastic solid. Don't worry too much about the technical details, but essentially it's a way of describing the energy density of a system.
Okay, it sounds complicated, but I'm with you.
Close showed how these wave equations could actually be used to describe the behavior of particles and their interactions. He even found that you could derive interaction potentials, the equations that describe how particles attract or repel each other from the phase shifts of these waves.
Phase shifts? You mean like when two waves overlap and they either amplify or cancel each other out?
Exactly. It's all connected. And here's the kicker in this alternate timeline. Dirac's famous equation, which is like a cornerstone of quantum mechanics in our world, still exists. But instead of being this mysterious fundamental equation, it emerges as an elegant approximation of a deeper, wave-based reality.
So even though the math looks familiar, the entire interpretation, the underlying philosophy is totally different. It's like we've lifted the hood on quantum mechanics and found a completely different engine running the show.
That's a great analogy. And it's even more mind-blowing when you realize that Dirac himself, in his later years, questioned the traditional interpretation of quantum mechanics and suggested that maybe, just maybe, the ether deserved another look.
Wow. It's like everything we thought we knew about the universe is being flipped on its head. But there's one more thing I have to ask about. What about antimatter? Where does that fit into all of this?
Excellent question. It ties into the concept of parity, which essentially asks, if you look at the mirror image of a physical process, will it behave the same way?
And in our timeline, the answer is usually yes, right? Except for when it comes to certain particle interactions.
Right. But Close challenges this traditional view of parity. He suggests that matter and antimatter are actually mirror images of each other, linked by something called spatial inversion. It's a bit too complex to get into here, but the takeaway is that in Close's view, what we see as a violation of parity in our universe is actually evidence for a deeper, more fundamental symmetry at play.
So instead of being this weird exception to the rule, antimatter actually helps to confirm Close's wave-based, ether-filled universe.
Exactly. It all ties together.
This entire deep dive has been absolutely mind-blowing. We've journeyed through an alternate history of physics where the ether isn't this discarded idea but the very foundation of reality, where matter dances to the tune of waves, and even the most bizarre quantum phenomena start to make sense. It really makes you wonder what other possibilities are out there, what other ways of looking at the universe we haven't even considered yet. Until next time.